So as wrapping up this chapter on chemical and phase equilibrium, a reminder, we're talking about reversible reactions. They have a symbol like this for what goes in between. We still talk about the side being the reactants and this being the products, but we often limit ourselves to 2 and 2. So AB for the reactants, CD for the products. Stoichiometric coefficients are the Greek letter nus. The equilibrium equation comes from quite a long derivation, but it's quite simple. It's the equilibrium constant, which is a function of temperature. And when you want that equilibrium constant, you have to really look for it out there in the literature. You can't compute it from first principles if you have information about Gibbs' free energy function. Okay, but most of the time when the problem is it's like, well, this is our reversible reaction. Maybe it's decomposition of nitrogen or this reaction equation right here. And you look up K, the equilibrium constant, as a function of temperature. You can put the equilibrium equation for the composition at equilibrium in terms of the Y's or the N's. Both of these are for ideal gases. We don't look at solutions that's not, I mean, you do that in the chemistry class, but here just ideal gas mixtures in terms of mole fractions or total amounts, N's. Everybody, I think, understands these terms. Those are stoichiometric coefficients, these N's raised to the stoichiometric coefficients, etc. True? We'll go ahead and just solve some clicker problems, okay? So I'll let you read it and enter your input. I'll give you a little more time than normal. All right. Polling has stopped. So let's see. What about CPS Energy? I know if you're not from San Antonio, you may not recognize it, but you do purchase electricity. There's not one person in this room who hasn't used some electricity. You've turned on a light switch, you've used electricity. All right? So, but this is the energy, electricity, and natural gas provider in this region. Well, what is the region? Basically the footprint of the city of San Antonio, but it's pushed out to the boundary, Bexar County. It's basically Bexar County in San Antonio. It services more customers than any other utility provider in the state of Texas. That's not true. There are some big utility providers up in the Fort Worth, Dallas area, TXU, as well as down in Houston area. It has the largest geographic service area of any. Well, that's probably some West Texas utility. It's got more acres or square miles. It has more coal-fired power plants than any other utility provider in the state of Texas. There's no information I have about that. I don't think that's true. Probably TXU up in Dallas, Fort Worth has a lot of coal-fired power plants. It is the largest municipally owned utility provider in the nation. Is it owned by the city of San Antonio? It is. That's what it means by municipally owned. And yes, it's very unique. It's the largest in the nation. So D is it. It owns and operates the largest nuclear power plant in the state of Texas. No. There are 4 reactors, 2 up at Comanche Peak, 2 down at Bay City. CPS owns nothing of those up in Comanche Peak, but it owns like a 43%, 44% share in the ones down in Bay City, if my memory's correct. It's around 40-some%. How many nuclear power plants are currently operating in the state of Texas? So what do we have? Well, we have 2 reactors at the site in Comanche Peak and 2 reactors at the site in Bay City. So that's 2 sites, 4 reactors total. So it's B. It's A. 4 reactors at 2 geographic sites. What in your lifetime will you probably see? 2 additional units at Bay City that was proposed, then all the natural gas coming online, dropped the price, shelved. plus Fukushima, plus some other things. It's all very political, but there's a lot of mechanical engineers employed in this area and will continue to be so. And I suspect more UTSA grads. There are current grads working at Bay City. I don't know of any at Comanche Peak. Effective January 1st, 2015. Hey, that was just a few months ago. The minimum seasonal energy efficiency ratio, SEER, for a split residential air conditioning system sold in the southeastern United States will be, what is that new minimum? All right, well, it is 14. That's what it bumped up to. If you're not in the southeastern part of the United States where you don't use a lot of air conditioning throughout the year, here in Texas we use a lot of air conditioning throughout the year. The state of North Dakota does not. State of Wyoming does not. A lot of other states do not. New Hampshire, Vermont, Michigan, then you can have a 13 SEER, but a lower efficiency because you don't use it much. But down here, you have to have the 14 SEER, effective very recently. Why has Refrigerant 12 and Refrigerant 22 been phased out of use in the United States? You know what I mean by phased out? Like, sorry, can't get it, can't use it anymore. A, they were too expensive since more economical refrigerants have been developed. They are harmful to the atmosphere. They are toxic and non-toxic refrigerants have been developed. They are flammable and non-flammable refrigerants have been developed, or manufacturers in Montreal and Protocol agreed to stop manufacturing them. All right, is everybody done? Well, this one is just has to go back, and you have to kind of remember, what did refrigerant 12 do that was so bad? It had basically chlorine in it. Plus it was very buoyant, so it went up, when it was escaped from the Earth's surface, it went up to high altitudes and interacted with the sunlight, busted apart, but then that chlorine gobbled up a lot of the O3, the ozone, in the upper levels of the atmosphere. Hence, you would get holes in the ozone layer, and the ozone layer is very important because it gobbles up a lot of the UV light. Well, if the ozone doesn't gobble it up, the UV light's coming down and impacting the Earth and it's hitting us as well. So that was the big push. Then also lately, global warming became more important, but at first it was more of holes in the ozone layer. Holes in the ozone. So it's harmful to the atmosphere. Basically, they had refrigerants which were extremely toxic before refrigerant 12 and 22. You could breathe 12 and 22 and still live. Other ones would kill you. A lot of people did die before 12 and 22, and those type of refrigerants were made. Also, they're not flammable. And their other predecessor were very flammable. A little spark, a little leak, and you have an explosion. There's not too many automobile accidents and have leaky refrigerants and all of a sudden blow up because of the leaky refrigerant. That doesn't happen. You don't even know about it. You don't even hear about it. So we're struggling to continue to have great low toxicity refrigerants and low flammability refrigerants, which are still environmentally friendly as well as affordable. So harmful to the atmosphere is the key. And especially, initially, ozone. Ozone way up in the sky. Liquefied natural gas plants are being constructed along the Texas coastline in order to import LNG or export LNG. We are basically now going to be an exporter. And there used to be federal laws against exporting oil and natural gas out of the state of Texas, out of the United States. They have to reverse those laws. And they have. Why is there a push to reduce CO2 emissions in the United States? I'll let you read those. Let me give you enough time to answer this. Well, it is definitely a greenhouse gas. They call it primary greenhouse gas, and it's definitely linked to global climate change. So it's E. Some people said C. What is C? Destroys the stratospheric ozone layer that shields the Earth from the harmful. Hey, isn't that the R12? That's what those refrigerants are being phased out for. Okay? Stratospheric, way high in the sky, ozone layer. Which fuel has higher CO2 emissions per kilojoule of heat released during combustion? Methane, hydrogen, gasoline, coal, or biomass? Which fuel has higher CO2 emissions per kilojoule of heat released during combustion? Oops, did everybody get in? I hope they did. So if you take a look, they talk about the state of Kentucky. I just learned this week, right? If you listen to the news and Obama's announcement, they said that in the state of Kentucky, where they still have a lot of mining of coal, also in the state of Wyoming, but in the state of Kentucky for sure, a huge percent of the electricity generated in that state is generated from coal. Like 98%. Well, because they have a lot of coal there, and then they dig it out of the ground, transport it to the plant, burn it, make electricity. Okay. But the CO2 emissions, CO2 initiative is going to really impact a state like Kentucky a lot, because they're heavy into producing coal, selling coal, using coal, and they want that to be reduced for the CO2 emissions. And so the big one, without doing any real calculations, is coal. Coal, 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 coal. Why do we remember Robert H. Goddard? He lived from 1882 to 1945. All right, well, Goddard. Why do we remember Goddard? Hydraulic turbines? No. Modern rockets. Exactly, modern rockets. NASA Space Flight Centers. One of them's named after Goddard. Why do we remember Josiah Willard Gibbs? Oh, they were too easy. There's no Gibbs temperature scale. Who is playing with me on that? All right, so it's thermodynamic relations and the Gibbs function and thermodynamics. He was from Princeton, and we still talk about him today in thermodynamics textbooks. What is a mini-split air conditioning system? Think about lights. When you walk into a house, do you have just one huge light switch and all the lights in the whole house go on? No. But you do have that for air conditioning systems. Why don't you have that for lights? Well, it'd be wasteful electricity primarily. And well, one of the ways to make the air conditioning in your home more energy efficient is to split up and have multiple units dedicated to parts of the house so you can turn them down or turn them off, because they don't use any electricity when you have the air conditioning system turned off, just like a light doesn't use any. So I think you're going to see more of these. I think the killer is upfront cost is more, and usually on a brand new home, people are very price sensitive, cost sensitive. It's like adding another $20,000, $20,000. Can I take that option out? Because I need to keep the price low. But mini split, they have multiple evaporators and one or very few condensing units. Okay. So the typical split system has a single evaporator, single condenser, but the mini split has multiple evaporators. Hey, how come we're so low on that? Did I tell you these were previous exam questions? They are. I'm not saying I'm giving you those this year. Didn't say that. But that's the type of question that you should be ready for, right? We covered those topics, did we not? All right, well, those are the multiple choice questions. Any comments or questions about that? I have some other problems I can go to solve. So a container initially has 1 kilomole of H2O gas, which can dissociate to form an equilibrium mixture of H2O, H2, and O2, in which the amount of H2O present is 0.9 kilomoles. So that's a long sentence. I'd break it down. I'd say this is what we initially have. This is what we have finally. All right. And I have so many kilomoles and so many kilomoles of what? H2O. And note that it's always gas. There's never going to be some H2O liquid. It's all H2O in the gas state. All of these behave as ideal gases. H2 and O2. So what does it start with? Well, it starts with 1 kilomole and nothing of the other two. What does it end with? Well, it ends with 0.9 kilomoles of H2O. Does it explicitly tell me how much H2 and O2 there is? Finally, no, but I can calculate that with a little work. So we go and we find our reaction equation, which is H2O dissociates to H2 and O2. Put a 1/2 right there. And that is in the header. That reaction is in the header of table 20, whatever it is, the back of the book in appendices. A27. That's in table A27. Okay. So for every one that goes that way, you produce 1 and you produce a 1/2. True? So how much actually went and disassociated? It started at 1, ended at 0.9. So 0.1 went that way. True? So 0.1 is produced, and 0.5, which is 1/2 times 0.1, is produced. So what do? Is we figure out that, oh, we're going to have 0.1 kilomoles of hydrogen and 0.05 kilomoles of oxygen. That 0.05, does that make sense? Yes or no? All right, good. So now we started with the total N of 1. We end up with a final total N of 1.05. Hey, you produced mass. No, you didn't produce mass. You produced more gas molecules, but the total same mass is there. You just disassociated a larger, heavier molecule and broke it up into 2 molecules. Or basically, for every 1 H2O broken up, you have 1.5 molecules of gas. Okay. All right. Plot the temperature of the equilibrium mixture versus the pressure ranging from 1 to 10 atm. What are they asking me to do? Plot the temperature, equilibrium temperature. Well, write down the equation for equilibrium for this reaction. Isn't it something like K, the equilibrium constant, is equal to, in the final equilibrium, the number of moles of H2 times the square root of the number of moles of O2 divided by the number of moles of H2O in equilibrium time the actual pressure divided by 1 atm divided by the totals N, all raised to the power 1 plus a half minus 1, or raised to the 1/2 power. I need to stop, my computer's acting up. Okay, so picking up now, what we have is we have the equilibrium constant, which we emphasize is a function of temperature, equal to the number of moles of H2, that's 0.9, times the square root of the number of moles of O2, 0.05, divided by the amount of H2O, this was 0.1, wasn't it? This is 0.9. And then we have the pressure to the square root divided by the square root of 1.05. I'm just putting in the numbers that we have. Okay? And so what we find is that's a constant. What is that constant? 0.0242 square root of p. So k is equal to blah, blah, blah square root of p. So if p is 1, then k is 0.0242. And so then we would look up and find, well, what temperature gives me a k of 0.042? So anyway, you build a little table. You build a table like this. The pressure and ATM. Let's put 1. Let's put 2. Let's put 3. All the way down to 10. Let's go ahead and put what is our k then. K would be 0.0242. Hence the log base 10 of k would be negative 1.6154. And then you go into the table A27 and you find the appropriate table. You find the appropriate temperature, okay? Let me show you for the second one. It would be 0.0343, negative 1.4648. Maybe jump down to 5, 0.0542, negative 1.2659, and then 10.0767, negative 1.1152. Okay? I have solved this in Excel and plotted it in Excel. So I don't recall what the temperatures are right here. But what is happening as the pressure goes up? What does the temperature have to do to maintain that fixed equilibrium composition? The temperature has to go up as well. Okay. And it goes up, you could see it. It goes up as it's kind of proportional to the square root of pressure. So it goes up kind of like that. So as the pressure goes up, the final equilibrium temperature has to go up too. Okay, so let's go ahead and take a look at it in Excel. Here is that plot, and here is the values of the temperature. It starts around 2800 Kelvin and goes up to 3160 some Kelvin at 10 ATM. All right, and when you plot it, there it is. Okay. You can't use Excel on the final exam, but you should be able to do the interpolation and find given, K, get T, given T, get K, both ways in table A27. Any questions about this problem? Does it look doable? Let's solve this problem then. Octane, which is C8H18, burns with 95% theoretical air to form an equilibrium mixture of CO2, CO, H2O, H2, and N2 at 2600 Kelvin and 1 ATM. Well, let's go ahead and get 100% theoretical combustion of octane and then modify it for the 95%. So C8H18 plus the right amount of air produces CO2. We can find that coefficient in front of the CO2 to be 8. And we can find the coefficient in front of the water to be 9. This is 16. This is oxygen. That's 25. So 25 divided by 2. And then we could put over here 25 divided by 2 times 3.76 N2. Okay, that's balanced for 100% theoretical air. True? No excess oxygen, but now we're going to modify it. We're going to say we're going to have C8H18, and we're only going to have 95% of what we need. Well, what did you need? That's what I needed. Okay. So I don't know how many CO2s are going to be produced. I think it's going to be around 8, but it won't be quite 8. Do you see it'll be a little less than 8? Because some of the carbon doesn't go to CO2, it also goes to CO. Whoops. CO. So we don't know how much, but the carbon's going to go either to CO2 or O2, but there's not enough oxygen around to make it go all to CO2. So there's going to be some, this number will be little less than 8, and this number should be greater than 0. All right. And then also H2O. Well, we'd expect it to be around 9. We'd expect it to be around 9, but it's going to be a little less than 9. And we're going to have some H2 floating around as well. And then how about the N2? Okay. How about any O2? Well, let's look at our problem statement very carefully. Yes, we expect the N2 to come out, and if you do the math on it, it's 44.65. That's how 44.65 is the amount of N2 that went in, that's the amount of N2 that went out. Is there any NO in the products? Or NO2 in the products? No. There's none described. Okay. How much, but what about the O2 in the products? Is there any oxygen in the products? We look carefully at our problem statement. They talk about CO2, CO, H2O, H2, and N2. They left out O2. Guess what? You have to leave it out too. So there's no O2 in the products. Why? Because the problem statement said there isn't. So there's no O2. So this is what we have. Now I have to say, I don't know how much. So what I'll do is I'll introduce, like the textbook, sometimes if you can do it without introducing these A, B, C, D coefficients, great. If you need to introduce them, like in this problem, you just have to introduce them. So let's introduce them. A, B, C, and D. I expect the coefficient A to be around a little less than 8. I expect the coefficient B to be greater than 0. It makes no sense to have a negative B, but not really tremendously large. Okay? I expect the coefficient C in front of the H2O to be less than 9, and D to be greater than 0, somewhere in there. All those coefficients need to be greater than 0. It makes no sense to have negative. Well, we need to have a carbon balance. So on the right-hand side, or left-hand side, we have 8 carbons, true? On the right-hand side, we have 1 for every A and 1 for every B. Is that a good carbon balance? You like that? Let's do the hydrogen balance. How many do I have? I have 18 on the left-hand side. I have none for every A, so let's not write 0 times A. Let's not write 0 times B, but let's write 2 for every C, and let's write 2 for every D. Did I write the hydrogen balance equation correctly? Then we have an oxygen balance. Well, I put the 0.95 times 25 over 2 times 2. So 25 times 0.95. 23.75. 23.75. Let me double check that. 25.95. 23.75. 3.76 times. No, now you got to back up here. Yeah. I'm sorry? Okay, you got 23.75. How many people got 23.75? Good. All right, and then how about over here? We're going to have 2 oxygen for every A. We'll have 1 oxygen for every B. We'll have 1 oxygen for every C and nothing for the D. Did we write that equation correctly? Okay, let me do this. Did anybody verify this 44.65? Is that correct? Good, thank you very much. Okay, now we have 4 unknowns. We have 3 equations so far. 1 from the carbon balance, hydrogen balance, oxygen balance. Where do I get a 4th equation? I have 4 unknowns. I'm looking for 4 equations. It's an equilibrium mixture that goes out. So we know we hope to look for an equilibrium constant. So this is our equilibrium equation, which would be a constant, a function of temperature. It tells us it went out at 2600 Kelvin, so there's our temperature. We could somehow get K if we knew what reaction equation to look for, is equal to, and then some equation. So what reaction equation do I look for that is in the play, so to speak, for having these products going out? Well, it's CO2, CO, H2O, and H2. I have to find one of those that are in my table A27 that has each of those 4 actors. So which one do I find? The very last one. So let me kind of write it up here. We'll have CO2 plus H2 is in equilibrium with CO and H2O. First time you see this, you say something's really wrong, but it's not wrong. This is the symbol, meaning it's in equilibrium. So in the final equilibrium mixture, I have some CO2, some H2, some CO, and some H2O. That's what I have. So what we have to do is we have to say, in the final equilibrium mixture, we're going to have the amount of CO, the amount of H2O, each of them raised to the 1 power, because that's the stoichiometric coefficient in front of that general dissociation equation. See that? There's a 1 here and a 1 there, hence there would be a 1 there and a 1 there. Okay, we divide by the amount of CO2 and the amount of H2, same thing, raised to the 1 power because of coefficient 1 and the coefficient 1 right there. And then we have whatever the pressure is divided by 1 atm, divided by the total amount, and the total amount, N, would be the sum of CO2, the amount of H2, the amount of CO, plus the amount of H2O, plus any inert gases, and the N2 is an inert gas, which is right there. And all of that's raised to the 1 plus 1 minus 1 minus 1. So in general, the inert gas, the nitrogen, which doesn't participate in the reaction, would be a player, except that this sum right here is equal to 0. Hence, pressure and the total N are raised to that power 0, and they just are all equal to 1 right there, that whole coefficient. Everything in this bracket right here is just equal to 1. So the final equilibrium equation in terms of our A's and B's and C's and D's is K times B, or B times C, divided by A times D. Do you see how that equation gets reduced? Make sense? Yes, sir.
Do you want to explain again about the power of the N?
Yeah.
Is it called
It's from the 1, the coefficient in front of the CO, plus 1, the coefficient in front of the H2O, minus 1, the coefficient in front of the CO2, minus 1, the coefficient in front of the H2. Yes?
Why are we using that one instead of like the CH, like the actual octane to get the K?
I'm sorry?
Why are we using the one on the corner instead of the one for octane?
Oh, right here?
Yeah, why are we using
Oh, it's kind of like everything combusts, but then it's coming out in a final equilibrium mixture. It didn't say that this input was an equilibrium mixture. No, no, no. But the outgoing gases are in equilibrium with themselves. So there's no more octane anymore. It's gone. It's been busted up into CO2 and COs. Right? And so, but now this is our very general dissociation equilibrium equation that matches our application problem, okay? Because if our application problem would have said, oh, we have some NO coming out and we have some O2 coming out in equilibrium as well, guess what? That throws a big monkey wrench into it. I'm going to have multiple equilibrium equations. It's covered in the textbook. We didn't cover it. It's just an add-on and mathematically much more complex. But before you make that add-on, what you'd want to do is just do the simplest, and that is saying, hey, you know what? There's only these coming out. An inert gas, N2 by itself, didn't react with anything. And then kind of the CO, CO2, H2O, and H2. Those four. And then you look in the table and you say, hey, table A27, those four players match that reaction equation.
And how can we take the nitrogen and found when we're doing some of the
For the total amount, right down in here, you have to include the nitrogen for the total. Even the inert gases, because they're in the gas mixture, affect equilibrium composition. Yeah. But it goes away because that exponent in this case is 0 to the power 0. So now I have 4 equations, 4 unknowns. Mathematician's done, but not the engineer. True? How am I going to solve for them? First of all, I get the K. So the K for this problem is the log to the power, it's 2600 Kelvin. And so it's to the power 0.802, positive 0.802. That's what K is. So I know K. I know 8 and 18 and 23.75. I just don't know the A, the B, the C, and the D. But those are my 4 unknowns, and I have 4 independent equations. Are they linear? Yeah. Are they nonlinear? Yeah. Because you have that multiplier in that last equation. It's algebraic nonlinear equation. So what's the strategy to solve? Can you solve this equation? Start substituting and reduce so that you can get it to one equation, one unknown. You just want to pick one, and you kind of look at it, and you know, okay. What I'll do is I'll try and put everything in terms of A. So I'll take the first equation, and I'm going to rewrite it. I'm going to say B is equal to 8 minus A. Every time I see B, substitute 8 minus A. Make sense? Take the next equation, this equation. Because I have A and I have B, I can get C. C is equal to, 23.75, right? Minus 2 times A minus B. But B is, well, let me do that. Then substitute for B right there. So you'll get 23.75 minus 2a minus 8 plus a. Okay? So what do you get? You get for C, you get 15.75 minus a. Whenever I see C, I can replace it by 15.75 minus a. I pause. I'm going to look for a few thumbs up if you follow and agree. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is everybody on board? See that? 15? Okay. All right. Now, what you could do is go back to this equation and you can get D. D is equal to 9 minus C. And C, we just worked out, is 15.75 minus A. And so this comes in at, what is it? Negative 6.75 plus A. I'm going to pause. Did I do that correctly? D is equal to that? Now we could take all that and put it down here. So we have 10 to the 0.802 is equal to B, 8 minus A, times C, 15.75 minus A, divided by A, times D, which is negative, well, whatever, you put A minus 6.75. Right there is one equation, one unknown. And I'm going to pause because I want you to get your calculator out that you're going to have on the exam tomorrow. And hopefully you practiced it already. And I want you to solve it. I want you to tell me what that A is. All right, this is one way to do it by hand. You have a function of A, and you want to drive that to 0. But the function of A is 10 to the 0.802 minus 8 minus A, 15.75 minus A, divided by A times A minus 6.75. See that? That's a function of A, and you want to drive that to 0. So make a little table, and the table starts like this. My guess will be 8. And then the function of A evaluated that guess, I have to get that number. It's not going to be 0, but get that number for me, okay? So let's go ahead and get that number. Well, first of all, it'll just be 10 to the 0.802. Won't it be 6.3387? All right, now this is the harder one. Guess an A of 7, and now evaluate that function. So we'll have do you get 1.3387? Yeah, I'm doing it by hand. Doing it by hand. Does that make sense? Now, let's just do another value. You could do a guess at this point by extrapolation. If I wanted to get a better estimate of the next A, it would be the next A would be it would be, let me do 8 minus, then you have 8 minus 7 divided by 6.3387 minus 1.3387. Did I do that interpolation right? What does that come out to be? Subtract reciprocal 0.2. No, this is not right, is it? Let's do it slowly. I know this is what I've got. I've got my function evaluated as function of A. When it's 8, it had a value of 6.3387. When it's 7, it had a value of 1.3387. I want to find where that goes to 0. That would be my next value. Okay. So what it would be, maybe do the next value would be 7, and then I'm going to do subtract the change, the slope. What is the slope? 6.3387 minus 1.3387 divided by 1 times the amount. I got to either divide by 1.3387. I think that may do it. Let me see what that is. That's 5, enter. 1.3387 divide. Change sign. No, that's too small. How come I can't do that linear interpolation fast? It's extrapolation, that's what it is. What is this value right here? The next value. We'll just do the slope. It's 5 over 1. The slope is 5. And I want to fall another 1.3387. So I would run a 0.26. So I would come in with 6 plus 6.732. Try 6.732. Okay, so we'll try that. 6.732. I got 100 point. No, that's not right. Just got to do it in Excel for myself. So much easier. This is the thing set up in Excel, okay? I know that you can't use Excel in an exam, but hopefully it illustrates. You have coefficient A, B, C, D. And over here is a little easier. So we put B is equal to 8 minus A. True? And then C is equal to 15.7 minus A. And D is equal to 6.75 plus A. And then what happens is the error is 10 to the 0.802, that part. Then you have the quotient there, subtract that off. And then what I did was I multiplied by 1,000. You don't have to multiply by 1,000, but it tries to exaggerate the size of it. And then you just start changing this. Let's say we started with a guess of 7, right? If you start with a guess of 7, well, it's not close to 0. But you use a root finder in data, what if analysis, goal seek, and it says take this value, cell H7, and you want to drive it to a value of 0 by changing this one, and then it does the work for you. So it should come in at 6.958. How many people had A around 6.958?
I got 6.7 something, 6.7045.
Your calculator should do a little better than that. 6.958 should be it.
You did what if analysis, and then you did what?
Yeah, but you can't do this on exam. But under the data table tab, come under what if, and pick goal seek. And then goal seek gives you sort of, you can take and iterate changing A to drive it to 0. The other one was we set up this whole function right here. All right, so now if I put in a C of 8, I get a value for that function 6.33 something, right? But I want to drive it down, so I put in the same function evaluated at 7, 1.3. Okay, so this function right here is evaluated using this value of A. I'm like building this table coming down. Well, let's try it at 6. What did I say I was trying it at before? 6.732. 6.732. And you just bring this equation down. And it is 100. I can't believe it. That's terrible. Right. But let's do this with 6.9. I'll sneak up on it a little better. Instead of 6.7, 6.9. Well, and then what you do is you just bring this down. Okay, so let's do 6.8. And that's not so good, so 6.95. Now I'm doing iteration by hand, and I'm not doing bisection. But when you get close, you should be able to do a little bit better. This would be 0.6. Oh, that's pretty close, huh? So there it is by hand if you don't want to use the calculator to iterate for you. But that's what the calculator is doing. It's trying to bracket it and iterate it. Last problem. I'm sorry?
It was
6.9. 6.958 for A. For B, C, and D are right there. So those are all that's all the answers. There's another way to solve this problem over here. I did it a different way. I used under data, I used this solver way up here. Solver lets you have to minimize something, and by changing multiple inputs. And notice it changed A, B, C, D. It changed all those inputs at the same time. And it minimized the equations I had below. But I had to put constraints saying, look, don't let these go negative. Don't let these coefficients go negative, because it was starting to make them go negative. So it had constraints. So solver is a little more powerful tool, but the equations I had was, this was my balance for, you could tell, it's the balance for the carbon, balance for the hydrogen. What did I just do? Mess that up? Escape. Hydrogen balance for the oxygen, and this was my equilibrium constant balance, K. I'm using K. And then if I start with, let's say I start with the 7, I got to turn this around. Start with a 7 and start with a 9, and then put, I don't know, a 1 and a 1 there. Okay, luckily the carbons are balanced, but not the hydrogens and not the oxygen, and definitely the equilibrium constant's not balanced. But these could be negative, like this is negative, or they could be positive. So what I do is I square them all, and then I add them up. And so it's kind of like, if they all go to 0, then the sum of the squares will all go to 0. And then I say, okay, come under Data tab, come under Solver. Under Solver, I already set this up, so I take cell D13, that's D13 right there. If you kind of click back and forth, it try to highlight it. D13. And then by changing these cells, A, B, C, D, subject to the constraints. Okay, there you go. So I say solve, and it actually did solve it, where all these equations are driven to 0, and the sum of the squares is all driven to 0. And there's the final solution. And this final solution here is very close to, if not the same as, this final solution over here for the same coefficients. So you could use goal-seek, or you could use solver in Excel if you had that in a project. All right, now let's solve a problem. So methane gas at 298, 1 atm enters a reactor operating in steady states. It burns completely with 100% theoretical air entering at the same temperature and pressure. The product's combustion exit at 900 Kelvin. Determine heat transfer from the surroundings to the reactor in kilojoules per kilomole of methane. Now, one of the things that help us is say, is this asking me to use the information of Chapter 13 on combustion or Chapter 14 on chemical equilibrium? It's really only a 13 on combustion. There's no chemical equilibrium, no K, no reaction equilibrium equation. So what do we have is we have an easy problem here. It's CH4, that's methane, plus oxygen coming from air, so it brings the nitrogen along. It goes to CO2, there's really only one there. It goes to H2O, there's two there to balance the hydrogen. And so when we look at it, we get two O2s. We need 4 oxygens. Leaving us then, let me see if I have my notes here, 7.52 N2s. So if you wanted to, you could clean this up just a little bit, and you say 2 O2s, 7.52 N2s, goes just like that for complete combustion, 100% theoretical air. What temperature do these all come in at? 298 Kelvin. What temperature do they all go out? 900 Kelvin. So what we have is we have a reactor. You have things coming in at 298. You have things coming out at 900 Kelvin. And normally we're going to put this Q dot. It's from the surroundings to the reactor, divided by N dot F. That's what we're asked to solve for. It's kilojoules per kilomole of methane. And we expect this to be a negative number in kilojoules per kilomole of the fuel. Why is it negative? Because it's exothermic. You're not only going to have hot products going out at 900 Kelvin, but you also have heat transfer out of that reactor. How much heat transfer? Let's calculate it. So how do we calculate it? We do a first law, energy balance for that reactor, control volume around that reactor. And we find that the Q dot divided by N dot F. Yes, that Q dot is positive in, even though we'd expect it to be negative, we write it this way, is equal to the sum of the products. What? The sum of the stoichiometric coefficient times the enthalpy of formation plus the change in enthalpy from 298 to the current outgoing product state, which is 900 Kelvin. Then we have minus the sum over reactants, stoichiometric coefficient, enthalpy of formation, and the change. Well, for this case, they're coming in at 298 Kelvin, so delta H for the reactants is 0. So this boils down to, when we expand it, the stoichiometric coefficient, enthalpy of formation, plus the enthalpy at 900 minus the enthalpy at 298, all of that for carbon dioxide. Same thing all of that for H2O plus the nitrogen. Now the nitrogen's a little tricky, so I like to emphasize that's the nitrogen in the products. And then we have minus over the reactants. We'll have stoichiometric coefficient, enthalpy of formation, and this will be for the CH4, the stoichiometric coefficient, enthalpy of formation, that's a minus. For the oxygen, for the nitrogen in the reactants. Okay, so why is the enthalpy formation nitrogen, hey, that's 0. Just like this is 0 right there, right? Same for the oxygen, 0. True? So let's start putting some numbers in. And so what we'll have is 1 CO2 times the enthalpy formation, negative 393,520. Then we'll have the molar enthalpy of CO2 at 900 Kelvin, 37405, minus the value at 298, 9364. That's good for the CO2. Now we go to the H2O. We have 2 H2Os. Enthalpy of formation, and that is H2O vapor. It's H2O vapor gas, so it's negative 241,820 plus 31828 minus 9904. And unfortunately, I have to scroll down the page because I ran out of room. And then we're going to have plus for the 7.52 nitrogens, 0 plus 26,890 minus 8669. And then we're going to have a minus 1 for the fuel methane. The enthalpy of formation, negative 74,850, close paren. So when you make that computation, you're left with negative 593,400 kilojoules per kilomole of the fuel, which is Q dot divided by N dot F. That's what we were asked to solve for. It is negative. There's heat transfer not from the surroundings into the reactor, but from the reactor to the surroundings. That's correct.
And then the molar, it's just a coefficient, it's not the actual moles?
Yeah, this right here, this N, is the stoichiometric coefficient divided by the 1 for the fuel. So you always leave a 1 in here for the fuel, and it's that coefficient that's in our balanced reaction equation.
So that little mole thing, okay, that's when I was working with power math, I was confused with that because I thought it would be in kilojoules.
No, N is dimensionless. That's right. Yeah. It's how many moles of each of the product per mole of fuel, how many moles of or kilomoles per kilomole of fuel.
Okay.
This is one question. Why temperature of reactor is equal to 0? Over 0?
Because it came in, the reactants came in at 298. They didn't come in hot or cold. They came in at standard 298. So
the question is kind of standard, it's not hot or cold?
most of the time they come in the standard condition. Most of the time. All it does is make for more tedious calculations when they come in hot or cold. And then also the fuel. A lot of times we don't have data on how bring in hot methane. Well, look all over this textbook all you want. there's a way of doing it, but it uses specific heats and it's a pain. Any other comments? Thank you for your attention. I'll see you tomorrow morning at 7:30.